Thank you. So let me talk about the topic of my session today is really interesting one because this is using C#, not as a high-level business development application system, but using C# actually for building system services, such as database system. This is what I do for a living. I do that in C#, or very high scale, very demanding system. So let me start by a quick introduction. I've been doing that for a long time, Microsoft MVP, and most particularly, I've been writing database engine for close to 20 years. And almost all of the time, I've been working in C#. In fact, this RavenDB is completely C# based. Now, whenever I talk to people about that, they say, why? Why would you want to do something like that? Especially because for a long time, C# was conceived to be the language that you use to build business applications. It's not what you use to build the actual platform. Well, here are a few things that are really interesting. First of all, C# is a high-level language. It's very easy to learn, well supported. Now this is cross-platform. But at the same time, C# has this breadth of views that allows you to do quite a lot of things with it. In particular, what it allows you to do, it allows you to control very accurately how memory and computation is going to work. C# has the concept of stacked value types, which allows you to do things on the heap, on the stack versus on the heap. It has support for direct manipulation of memory. I'm not sure if you are aware of that, but C# actually have pointers and pointer arithmetics, which means that certain patterns of behaviors that you might have encountered in high-performance system in C or C++ are directly translatable to C#, but with all of the benefits that you have. Just to give you some idea, this is the Tech and Power benchmarks. And you can see here that ASP.NET is the #2 space on this guy only just barely edged it. And for the past 5 to 7 years, Microsoft has been, and the overall .NET community has been putting a lot of effort into improving performance. And that has significant benefits all around. So let's talk about this. Whenever I tell people that I'm writing a database in C#, they go, what? Because there is this conception that, oh, for system services, you have to use an unmanaged language. You have to use something like C, C++. Now Rust and Zig have come into the fore, but why would you want to do that in C#? Well, it turns out that managed languages have some advantages, and specifically managed languages, when you're working in a managed language called C# has even more. So there have actually been quite a few benchmarks where Java is faster than C. And why is that? Because Java has more information. It is just-in-time compiler. So it has more information about what's going on. It can make better optimizations. So let's look at what I need to build system software from my platform. And this is where we started. In 2002, that's 20 years ago, as scary as that sounds, we had value type and stacks, unsafe code, pointers, and native memory allocations. And I actually built a database just using those features. But now it comes to more interesting things, because now we have a lot of other features in C# specifically to implement those sort of things. And the span of T and memory of T and all of that allows you to work with memory in a manner that is as efficient as if you're working with native memory, but all of that is managed. You have access to vector instructions, to all of the hardware built-ins. And I think that the primary focus was the fact that the Microsoft open source.NET and accepted community contributions, at which point something really interesting started to happen. And that something is that every little annoyance that someone had got removed. Oh, there is this extra allocation here. I can make it 2% faster here and stuff like that. But those sort of changes started to pick up, and that had a tremendous impact all around. Now, so far, I've been just talking in the air. I want to give you some concrete values. So let's look at this. I decided to implement a Redis clone in C#. And this is roughly what the Redis text protocol looks like. You have a star, and you can ignore the white space. This is just to make it easy. You have a star, and then a number, and then a line break. And this indicates that there is an array of objects of length of 2, then $3, which this indicates a string, and the command, and line of 3, and end of line, and etc. So what this basically says is I'm sending a command that has 2 items. The fourth one is get, and the second one is order, and then I have a Oren, then I have to process that. Now, the question here is, what would it take to build something like that? Something that just read and write data in memory, just like Redis, in C#. So this is what we have. And this is something that I built in as naive a manner as possible. Just to give you some idea, this is under 100 lines of code. And I just want to take you through this. So I'm opening a TCP listener, and I'm creating an instance of this class. And what I'm doing here, I'm basically saying accept TCP client, and then handle the connection. Handle connection is an async task, so this is running in the background. And in here, open a stream for reading and writing, and basically just read. This reads the array, this reads the first command, and eventually I'm getting this thing. So this is basically a very manual, very obvious, trivial code parsing. And there is, I decide how to write the data back. I'm flashing the data to the user. And this is pretty much the actual code. This is the actual heart of the system, where I'm executing the get command or the set command. This is actually gets stored inside of a concurrent dictionary. And okay, and that's about it. Notice that in terms of concepts, we may have multiple clients running at the same time. We may have concurrency between them, which is handled by concurrent dictionary, and all bunch of other stuff like that. 100 lines of code. There is nothing here that is interesting or surprising. And I decided to test that in production. I got an instance from Amazon, a 66G. This is an ARM system. So 16 core, 64 gigabytes of memory, and I used the Redis benchmark utility to try to hammer it out, to see how much performance can I squeeze out of that. And I got to nearly 1 million queries per second. And think about what this means. I spent an hour building that. Most of the time was spent on figuring out what the Redis protocol actually looked like. And now I can hit close to 1 million. Now, make no mistake, this is absolutely not a high performance option. There are many issues here that cost us quite a lot, even though the amount of code that we have is minimal. But that's the fun part, and one of the things that I like about C# that I have the options. So I decided to take it further. And I decided to see, okay, what happens if I don't do the naive thing? What happens if I start doing things slightly more in a slightly more sophisticated manner? So now you can see that I have, here is the state. Here I'm accepting the TCP listener, passing it to a client. This is just error handling, doesn't really matter. And now, here things start to be different. Instead of using a stream reader, I'm using something called pipe reader and pipe writer. Those are built-in classes in the framework that allow me to do some really interesting things in terms of reading and writing from a stream or the network. Basically, and you can see it here, I'm going to the network net reader, and I'm saying, read something from the disk. And this is interesting. Notice that I'm not actually reading here. I'm saying start the reading process. And here I'm saying, well, here is a negative flash, something. You know, here I'm waiting for the reading to complete, this read to complete. Once I've done that, I'm calling to parse network data. And I'm going to go over that in a bit. But the key here is that what I have here is in-memory data, in-memory buffer that I got from the NetReader, and I'm going to operate on that. And this is doing all of the work without using any allocations, with great support for pipelining. So if I have a command, may send multiple commands at the same time. It also has great support for doing things like what happens if I have a partial command. So I read a buffer, and the buffer contained only the first two lines here. So I know that I have another object that I have to read. So the pipeline API, the pipe reader API gives me a great support of doing that. And you can see that the sequence reader that I'm using here allow me to search for a byte /n, so I know how to read that. And the whole thing isn't that much more complex. The total cost that we have almost double, but we'll see why in a bit. Now, so I read and execute the thing. And then now notice what I'm doing here. I'm saying here that this is how much I consume from the stream, and this is how much I examined. Because again, if I'm looking into this guy, so into this guy, and I read up to here and I still need more, then I didn't consume anything from the network, but I examined up to here, so we tell the pipe reader that I have to read it again. And now I'm doing something really fun. I'm telling it I need to read more, but I'm not waiting on that. And I'm flashing to the network, but I'm not waiting on that. Instead, I'm waiting on that on the next round. So I'm actually parallelizing both the writes and the reads to the server. You can actually see what I'm doing here when I'm executing the commands. So again, the code here is slightly more complex because I have to deal with doing the work without doing any additional allocations. And here I still have to do some work, but basically here I'm writing. And this is really interesting because look what happened. I'm asking the writer, give me some memory. And then I'm writing to this memory, and this is a pure in-memory operation. And then I'm advancing that. And at some future point in time in here, I'm going to flash that to the network. So, and that's about it. I have here some other helpers, but nothing really that interesting. So this is the naive version with 949,000 queries per second. And I spend a bit more time and I reach 1.6 million queries per second. Now I can take it further. I can go here and apparently not this one, this one. And now I can do this. Instead, if you will look here, you will see I'm still using a string here. So I have to allocate that. Instead of using a string, I can use something called a usable buffer, control its allocations, and now I don't have any string allocations to work with, which means that we are now at 1.8. And all of these codes, we started from under 100 lines of codes. The top version that I have is under 400s. Now, we can push it to 2.5 if you go really crazy. But then you realize that where are you spending most of the time? You're not spending most of the time doing actual work. You're spending most of the time waiting for I/O. So now you have to figure out, how am I actually going to operate with that? How can I move forward? Well, the API that I got is whatever I get from the TCP stream. That's it. And then I put a pipe reader or pipe writer on that. So, okay, so is that what I'm limited for? Well, no. If you are familiar with high-performance systems, you know that there are multiple ways of managing I/O. And one of the best options for managing I/O in Linux today is something called I/O U-Ring, which is an interesting system where you schedule the operation to happen completely without writing to the kernel. There is this buffer, ring buffer that is shared between the kernel and the user space, and you have almost zero system call overhead. And you can use that in C#. There is a NuGet package that you can use, which is, if you think about it, this is quite insane, because here I am working in C#, but I'm able to use this low-level interface that is meant to be consumed from C systems that are crazy, C application or C servers, C written servers that are written to extract the maximum amount of performance from the system. I'm not limited. Now, I could go on and talk about all of those options. The fact that you can go and control your memory is huge, because one of the key costs that you have with C#, with any managed language, with any system, is how do you manage the cost of allocations? Because eventually you have to deal with things like, in a managed language, the garbage collection. In an unmanaged language, fragmentation, allocation frequency, or much further stuff like that. With C#, you have the option of saying, hey, I can use native code. Or alternatively, I can use managed code. And you can also marry the two together. In here, I'm saying something interesting. I'm saying this is a buffer that is coming from an array pool. And I can utilize the finalizer to return it back to the pool when it's done. And that means that I can suddenly have a GC cover my track. One of the most complicated things about writing correct memory safe code in native languages is handling all of the error conditions. What happens if you hit an error while you're handling an error? Did you free all of the memory and all much of other stuff like that? With C#, you can use native memory. You can allocate it free at the same time, but you can also set it up in such a way that if you forgot to do that, then C# with the garbage collection would go and clean it up for you, which means that a huge chunk of complexity just goes away. We actually use this feature quite extensively inside of RavenDB to get the benefit of both worlds. We have something that is invisible to the GC, so it doesn't, the GC doesn't try to collect that. But at the same time, if we manage to screw up and didn't release something, our bugs are covered. There is another aspect that you have to consider. The typical issue in most systems is that you have very specific hotpots that you have to look at and optimize. And the more work you're doing in particular area, the better it is to sit and optimize the hell out of that. At the same time, most of your system is run very, very rarely. If you're using something like C to write your system, you have to take the burden of building to that level of manual work each and every time. You have to control all the fiddly bits. With C#, I get to decide whatever I want to be at a high level. For example, I reading from the config file. I do that once in the application. I have zero interest in its performance. I want to be as high level as possible, as safe as possible of that. That piece of code, that index document, that piece of code that process the request from the network, I want to be able to control where every bit and byte goes. So you get to the point where you have this interesting option of this range. Oh, this isn't really that interesting. I can write it in a quick and dirty way and not care. Really interesting aspect of that, and something that we actually use many times, is that you have the option of also building the system in a almost rendering manner. So you start by writing it like this. And this is almost at the level of pseudocode as far as I'm concerned. This is directly what we want. And then we write it again using the lower level API. And there are still additional steps I can make to make it more efficient. But it is about accepting the cost-benefit issues, because you have to deal with cost of development versus the cost of runtime. And in many cases, this is a real tension. Sometimes you want to optimize for development. Oh, I have a feature, I need to get out. Sometimes this is my core, this is what I do to make things interesting. And then you get to write the most specific thing ever. Now, I want to show you some real world code and to give you some indication about where things are going. This is the RavenDB code base. And here we go. So a few things to notice about this code base. You can see this is a struct. So we are actually allocated on the stack. There is no allocation in here. And we have this really interesting aspect of multiple generic parameters. One of them, by the way, and have a lot of limitation. What this piece of code saying, this is a number. I can do a plus on that. I can do a greater than, less than, stuff like that. But I want you to focus on this aspect, the high and the low. And the reason they exist is because we have this code. If type of tlow is exclusive, run this check. Otherwise, skip it. And now, if do a comparison, and if this is exclusive, run this check. If this is inclusive, run this check. Now, here is where it gets interesting. When the JIT compiler for C# sees this code, it knows that it's generating the code for a specific version. For example, for this version. But this is still generic. So let's go up. So now you can see that this is, both of them are inclusive. What about this one? This is exclusive and inclusive. So at this point, this is exclusive. The JIT knows at compilation time, because it knows what the type is, that this is exclusive. So it needs to run this check. But if I'm looking at the between query, this would be an inclusive check. This would be false, and the JIT compiler will not even emit the output. So now we are operating at a very high level, and we are using tricks that are applicable to generic template metaprogramming in C++ to control and optimize branching and all sorts of other stuff like that. So something really important about that. This is absolutely a trade-off. But this is trade-off I can do not globally, very, very specifically. And if I'm looking at the overall cost of building something in C++ versus C#, just the compilation time of C++ means that I'm going to be faster all around, if only because my feedback loop is so much faster.